The title of my talk is Sensitivity Lower Bounds from Linear Dependencies. I am Anupa Sunny, and this is a joint work with my advisor Sophie Laplante and Reza Nasserazid. The focus of this work is to take another look at Huangs' breakthrough result that solved the sensitivity conjecture and to get more structural results about the sensitivity of a function. We will start with a few definitions that will be useful in this talk. A Boolean hypercube or Hn has as its vertices n-bit strings. Two vertices u and v are connected to each other if and only if they differ at exactly 1 bit. We denote the set of vertices with odd Hamming weight, that is vertices labeled by strings with an odd number of ones, by u odd. Similarly, we denote the set of vertices which corresponds to strings with an even Hamming weight, by u even. The hypercube is a bipartite graph with one part being odd vertices colored blue and the other being even vertices colored red. A Boolean function takes as input n-bit strings and assigns zeros or ones to them. We can think of it as being embedded in the hypercube, with each vertex now being assigned either 0 or 1. The figure shows an example of a Boolean function. An edge in the hypercube is said to be sensitive if its endpoints are assigned different function values. In this figure, the graph induced on the vertices that are shaded gray consists of only sensitive edges. Sensitivity of an input x with respect to a function f is defined as the number of bit positions I such that f of x is not equal to the function value at the original string with the ith bit flipped. Therefore, the sensitivity of an input is the degree of the corresponding vertex in the subgraph with only sensitive edges. Sensitivity of a function is the maximum sensitivity over all inputs x. Now we will define the zero sensitivity and one sensitivity of a function. We define zero sensitivity of a function as the maximum sensitivity over all inputs that are mapped to 0 by the function. Similarly, one can define the one sensitivity. Now we will try to define the block sensitivity of a function. To do so, we first define the sensitivity of an input to a block. Here a block is any subset of bit positions, not necessarily consecutive. For a set B, which is a subset of the set 0, 1 to n, an input is said to be B sensitive if the function evaluated on the input with all the bit positions in the block B flipped is different from the original function value. In this graph, the function maps the vertex 0, 0, 0 shaded gray to 1. This input is sensitive to the block 2, 3, as on flipping both the second and the third bit, you get 0, 1, 1 shaded yellow, which is mapped to a different function value. The block sensitivity of an input is the maximum number of disjoint blocks such that the input is sensitive to each of these blocks. Here we have shown an input x and have marked some disjoint blocks that x is sensitive to. If this is the maximum number of disjoint sensitive blocks for this input, then its block sensitivity is 2. We define the block sensitivity of a function as the maximum block sensitivity over all n-bit inputs. By definition, block sensitivity is larger than sensitivity. The sensitivity conjecture, as posed by Nissan and Szegedy, was that block sensitivity and sensitivity are polynomially related. That is, block sensitivity is upper bounded by sensitivity to the power c, where c is a constant greater than or equal to 2. Now we look at a complexity measure of Boolean functions that played an important role in showing a polynomial relation between sensitivity and block sensitivity, and this is the degree of a function. This measure is related to representing Boolean functions using real polynomials. We say that a real n-varied polynomial p represents a Boolean function If at all the 0, 1 to the n inputs, the polynomial evaluates to the function value at that input. There is a unique multilinear polynomial representing the function, and its degree is called the degree of the function. When a function has full degree, that is, when its degree is equal to n, it imposes certain properties on the hypercube restricted to the sensitive edges. Recall that the edges in the hypercube are between odd vertices and even vertices. As shown in the figure, the vertices of the hypercube can be arranged in layers based on their Hamming weights. The vertex in layer 0 has Hamming weight 0, vertices in layer 1 have Hamming weight 1, and so on until layer n, which has the vertex with Hamming weight n. Alternate layers have opposite parity with respect to Hamming weight. We also partition vertices in each layer such that the vertices on the left are mapped to 0 and those on the right to 1. The set S consists of odd vertices that are mapped to 0 and even vertices mapped to 1, and this set is colored blue. The set S prime, which is the uncolored part with odd vertices that are mapped to 1 and even vertices mapped to 0. So sensitive edges go between vertices in S or they go between vertices in S prime. As was shown by Gaudsman and Lineal, when a function has full degree, either the set S or S prime has strictly more than 2 to the n-1 vertices. With the basic definitions set up, we will look at some of the theorems that help to prove the sensitivity conjecture. In 1992, Nissan and Segedi showed that for any Boolean function f, block sensitivity of f is at most 2 times degree squared. The proof of the Nissan and Segedi theorem uses symmetrization of polynomials and Markov's theorem from approximation theory. Also in 92, it was shown by Gaudsman and Lineal that the following two statements are equivalent. The first statement being that the sensitivity of a function is lower bounded by square root of the degree of the function. And the other statement being that in any induced subgraph G of the hypercube with strictly more than half of the vertices, that is more than 2 to the n-1 vertices, there exists a vertex with degree greater than or equal to root n in either G or its complement. The original Gaudsman and Lineal theorem works for any monotone function H. Here we have chosen the square root function. To prove the Gaudsman and Lineal theorem, it is enough to show that the second statement is equivalent to showing that the sensitivity is at least square root n for a full degree function. For a full degree function, the set S or S prime defined earlier has more than 2 to the n-1 vertices. We also know that all the edges in this graph are sensitive edges. So by proving the existence of a high degree vertex, it proves the existence of a highly sensitive input. Huang in 2019 proved the second statement, hence giving a proof of the sensitivity conjecture. Now we will look at a proof of Huang's theorem. Huang considered a signed adjacency matrix A of the hypercube such that A square equals Ni. Let sigma denote a signature that assigns plus or minus signs to the edges of the hypercube and 0 otherwise. It can be seen that the only property that the signature sigma needs to have for the signed adjacency matrix A to satisfy A square equals Ni is for it to assign a negative sign to every force cycle. Here the sign of the force cycle is the product of the signs of the edges of the force cycle. The figure shows how such a sigma can be inductively constructed. A red edge denotes a negative sign and green denotes positive edges. Take a smaller hypercube satisfying the property that every force cycle is negative. Now take another copy of this smaller hypercube with all of its signs reversed. This retains the property that every force cycle is negative. Connect the corresponding vertices in these two copies by a matching of positive edges. This hypercube now satisfies the property that every force cycle in it is negative. The original proof by Huang uses the interlace theorem, But we will now look at a different proof which associates a vector to every vertex in the hypercube. Then we will look at linear dependencies in the set of vectors corresponding to the subgraph and give structural results about the sensitivity of a function from these linear dependencies. Now that we have a square equals ni, we have that a plus square root ni times a minus square root ni is equal to 0, which implies that the row space of a plus square root ni is orthogonal to the column space of a minus square root ni. Since both of these are subspaces of R to the 2 to the n, one of these subspaces has dimension less than or equal to 2 to the n minus 1. We now assign a vector to every vertex in the hypercube. If the smaller of the subspaces is the row space of a plus square root ni, we assign every vertex x a row of this matrix denoted x plus. Else we assign to every vertex x a column of a minus square root ni denoted x minus. Here we can see that at the x entry of the vector, we give plus or minus square root n. At all the other entries y, we give sigma of x comma y. This means that the entries corresponding to neighbors of x are assigned plus or minus 1s, and those corresponding to non-neighbors are assigned zeros. Now, without loss of generality, let us assume that the smaller of the subspaces is the row space of a plus square root ni, and that we have assigned x plus vectors to every vertex x. Recall that Huangs theorem states that if we have more than 2 to the n minus 1 vertices of the hypercube, then the induced subgraph on these vertices has a vertex of degree at least square root n. Since the subspace spanned by x plus vectors has dimension at most 2 to the n minus 1, and since we have more than 2 to the n minus 1 vertices in the subgraph, the x plus vectors corresponding to the vertices in the subgraph have a linear dependency. We will now prove the following observation, which gives us a high degree vertex from linear dependencies. If a set of x plus vectors, say x1 plus up to xk plus, has a linear dependency, then the subgraph induced on the corresponding set of vertices x1 up to xk has a vertex of degree at least square root n. The proof is the following. Since we have a linear dependency, a weighted sum of the x plus vectors with a coefficient ax is 0, where not all of the ax's are zeros. Let ay be the coefficient with the maximum magnitude over all the ax's. Then at this coordinate y, we have from the linear dependency that the contribution from y plus vector cancels those from the other x plus vectors. Recall that in an x plus vector, the only non-zero entries are at the coordinates corresponding to itself and its neighbors. So we have that ay times square root n is equal to sum over all neighbors of y, sigma xy times the coefficient ax. When we take the magnitude value, this becomes an inequality as the signs can be negative as well. Since ay is the coefficient with the maximum value, we get that this is at most sum over neighbors of y, magnitude of ay. Thus, y has at least square root n neighbors. Recall that this induced subgraph that Huang's theorem starts off with has odd vertices with a certain function value and even vertices with the other function value, and hence every edge in this subgraph is a sensitive edge. The degree of any vertex in this graph equals its sensitivity, and this gives us that the sensitivity of this high degree vertex is at least square root n, completing the proof of the sensitivity conjecture. Next, we will see how we can get more structural results about the sensitivity of the function using this technique of assigning vectors to the vertices of the hypercube. But we will need a few more definitions. We say that f is a non-trivial linear dependency if sum over u plus vectors of odd vertices weighted by au equals sum over v plus vectors of even vertices weighted by bv, and not all of the AUs and BVs are zeros. Here we have just separated the coefficients by assigning a's to odd vertices and b's to even vertices. Let HF denote the subgraph induced on vertices that have a non-zero coefficient in the linear dependency F. The figure shows such a linear dependency F and considers the subgraph HF, which consists only of vertices with non-zero coefficients in F. Since x3 does not appear in the linear dependency, it is shown using dotted lines. NF of x denotes the set of neighbors of x in HF, and let df of x denote the degree of x in HF, that is the size of the set of its neighbors. Here, x1 and x2 form the neighborhood of x in HF, as x3 does not belong to HF. The degree of the vertex x is 2. N2f of x denotes the set of vertices y that are at distance 2 from x and has a unique path in HF from it to x. Here, x5 and x6 form the N2f of x, as there is a unique path from x to each of them through x1 and x2 respectively. But x4 does not belong to this set, as there are two paths in HF from x4 to x. The main theorem we have is the following. Given a non-trivial linear dependency relation F, there exists an odd vertex u and an even vertex v in the subgraph HF corresponding to this linear dependency, such that the number of neighbors of this vertex plus the number of distance to neighbors with a unique path to it is at least n. This holds for both u and v. As a corollary, we get that if F is a non-trivial linear dependency, then there exists an edge in the subgraph HF such that the degree of u times the degree of v is at least n. Now we will look at a proof of this corollary. Our theorem states that there is a vertex u such that the number of neighbors of this vertex plus the number of distance to neighbors with a unique path to it is at least n. If the degree of this vertex is d, then there exists a neighboring vertex v such that it has at least n minus d by d vertices in the second neighborhood of u. Thus, the degree of this vertex is greater than or equal to n minus d by d plus 1 when you count u, and this is equal to n by d. This gives us that the product of the degrees of the vertices u and v is at least n. This corollary gives us the result that the degree of a function is at most 0 sensitivity times 1 sensitivity. This follows as the vertex's degree in a graph with only sensitive edges corresponds to its sensitivity, and two vertices that are connected to each other are mapped to different function values. We need the following lemma for the proof of our theorem, which states that given a linear dependency F, which can be expressed as a linear combination of odd vertices on the left and even vertices on the right, we can say that for all odd vertices x in the subgraph HF, n minus the degree of x in the subgraph times the coefficient ax is equal to the coefficient az summed over the second neighborhood z weighted by the signature of the unique path from x to z. The signature of this path is given by the product of the signatures of edges that form the path. A similar statement holds for even vertices as well. Once we have this lemma, our theorem, which states that there is an odd vertex and an even vertex such that the number of neighbors of this vertex plus the number of distance to neighbors with a unique path to it is at least n, follows naturally. We take the coefficient with the maximum value in magnitude and consider the lemma for that corresponding vertex. Then by ignoring the signs and by replacing other coefficients by the maximum coefficient, there should be at least n minus degree of x non-zero contributions from the right-hand side. And thus there are at least n minus degree of x many distance to neighbors with a unique path to x. An analogous argument follows for the even vertices. This completes the proof of our theorem. To conclude, we have assigned vectors to vertices and studied resulting linear dependencies and their implications at distance 2. This improved Huang's degree bound to the product of zero sensitivity and one sensitivity. There are several interesting directions to pursue, such as the implications of linear dependencies at distances greater than or equal to 3, and similar techniques for bounds between other complexity measures. The quadratic sensitivity conjecture, as originally posed by Nissan and Segedi, remains unsolved. Thank you.